Good morning. I'm here again to introduce the last session of the morning of our conference. This is the planet-centered computational math. And in general, this session is focused on addressing problems at a large spatial and or temporal scale, and typically require holistic views to understand both the questions and that we're asking, and also to assess the effectiveness of our solutions. Challenges in the field of energy generation, harvesting, transportation, emission reduction, climate change, among others, are all in this category of problems that we face. Now, research at the planet scale requires both a detailed fundamental understanding of the physical process at play, and also a system-level view of the coupling and the life cycle impact of our imagined solution or proposed solutions. This is obviously a sweet spot for ICME, enables us to bridge the disciplinary knowledge that is typically present and available across campus in the various departments, but then with our own ICME interdisciplinary approach. It is also typical to engage with national laboratories, NGOs, research organizations to address long-term research that can really impact these issues. Typically, short-term solutions are not quite as effective for addressing these kind of issues. And especially for issues that might be very near and dear to our hearts, like climate and the impact of extreme events and so on. Now, the current research in the frame of planet-centered areas focuses on a variety of tools. Typically, they're anchored by physics-based simulations, so what we refer to as first principle analysis. So these are simulations that are based on all our current understanding of the physics and try to really represent the processes at play directly. But then they include, obviously, high-performance computing, algorithm development, more and more recently, data science, uncertainty quantification, but a general approach that involves deep innovations, both in algorithms, in software tools, and eventually in data, in approaches to data. In this session, we are going to have 3 presentations that cover a really broad spectrum of different topics, focus both on algorithm and software development to address general problems that have to do with energy, transportation, and analysis of physical systems. And this is the talk by Professor Eric Darve. The second talk by Professor Jenny Sokali discusses these sort of extreme events and hazardous events, and how simulations can help sort of understand the dynamics and the details of how these events might occur and what the risks associated with it are. And then the final discussion, the final talk is about managing water and water resources in the planet. So very exciting session, and I think a fitting end to our morning sessions. Now, just to let's get started with our session. Then I want to give first a brief introduction to our first speaker, which is Professor Eric Darve. Eric has been a member of ICME from the very beginning. I think he was together with Eric Schachfe. We heard this in a previous session, was one of the first acting in ICME and working in developing the curriculum. He received his PhD in applied mathematics from the Pierre and Marie Curie University in Paris, working on fast multiple methods. Previously was a student at École Normale Supérieure in mathematics and computer science, and arrived in US as a postdoctoral fellows, joined with NASA Ames in 1999. And has been since a great member of the faculty and a fantastic asset for ICME. Eric, take it away.
Yeah, thank you for giving me this opportunity to present a little bit some of my research in the area of machine learning. So this joint work with Adrian Liu in mechanical engineering and our joint PhD student Grady Wong. So I want to talk about. So there's a video on the top right. Probably with Zoom, it's not working too well with the lag, but it's showing you the industrial process called 3D metal printing, so or selective laser melting. So you have a laser that basically is melting a powder bed with metal, and you can use this process to build arbitrary 3D shapes made out of metal. But this is a process that's still very, very tricky to control, and very often the manufactured parts are of poor quality. They can bend, they can fracture, and there's a lot of internal stress, typically residual stress after the printing process that kind of weakens the parts. And so here we're interested in this product. We're interested in optimizing the path of the laser on the powder bed in order to reduce this residual stress and improve the quality of the of the printing. So we're using a PD model, so just a diffusion reaction equation. So of course you can have more sophisticated physical models, but we started with something that would be a simple model for the evolution of the temperature. So you have a source term here. So hopefully you guys can see my mouse. You have a source term, which is basically the laser that's hitting the metal, and then it generates heat and raises the temperature, and then this temperature kind of diffuses throughout the part. And so the goal is to basically optimize the path of the laser in order to maximize this objective function. And the goal is basically to try to maintain the temperature above a given threshold for as long as possible. So the way we solve this problem is through combinatorial optimization. So this is showing a schematic of the surface of the 3D printing bed so the powder bed that we're using for printing. So just a 2D surface, and the laser is kind of moving across the surface. So what we did is we discretized the surface into tiles, and then we're assuming that we are shining the laser on a given tile, and then moving to a different tile. And so the path planning now becomes a sort of combinatorial problem of essentially selecting the ordering of these tiles that will maximize our objective function. So this is a goal: visit all the tiles once and optimize the sequence of tiles in order to maximize our objective function. So this is a combinatorial optimization problem with a cost function that's basically defined by our partial differential equation. So we leverage some techniques from reinforcement learning and deep learning. So in fact, we were inspired by the techniques used in AlphaGo. So this is a method that uses a Monte Carlo tree search, so as shown on the left. And then there is a neural network that's trained to predict the correct policy and the correct value. So basically, we're trying to determine in this tree what is the optimal path, and this, in our case, this will determine the permutation or the path of the laser. So unfortunately, we don't have the resources that Google has when they were benchmarking AlphaGo, and so we had to make some changes to the algorithm in order sort of to reduce the computational cost and make it tractable on our more modest computational resources. So we still are leveraging this Monte Carlo tree search approach and deep neural network, but we only use it now to generate what I call the current best guess. So this is sort of an intuitive process. And so this is the current iteration, what our best guess is. And then we use a local permutation strategy called kopt to generate a permutation set, so a large set of permutations, and that some of them will improve upon this best guess. But the key take-home point here is that this set is actually used to retrain our deep neural network. So it becomes a new training set for our deep neural network, and so we update our deep neural network based on this improved permutation set that was generated with kopt, and then we go back to step one. So we have this loop where we use our MCTS and DNN to generate our current best guess, use kopt to generate a new training set, and then based on this training set, improve our deep neural network. So I just want to show some numerical benchmarks. So we compared against the R2 algorithm, which is basically follows very closely the AlphaGo algorithm, and so tends to be more expensive because it doesn't have this sort of k-opt optimization. Then we compare against 3-opt. So this is basically k-opt with k equals 3. So we're permuting 3 elements. So this is a very simple strategy, sort of not very smart, but it's very, very fast. So it can still do reasonably well. And then the last one was a model predictive control, where basically we run some optimization based on a limited horizon. So this is what the results look like. So our method is the blue curve here, and this is the size of the board: 4x4, 5x5, and 6x6. So here, for example, you have 10 to the 41 permutations. So you cannot enumerate all the permutations for this this board, and you can see that our method is doing quite well. We're almost 15 sigma away from the mean, and we're significantly outperforming the other techniques. All right, so this concludes my talk. Thanks for listening.
Thank you very much, Eric. Thank you, Eric. This was a great, fascinating talk. Let's move to our second speaker. I just want to remind everybody to post questions on the Slack channel, and we'll address all the questions at the end of the session. I forgot to mention this before. So our second speaker is Professor Jenny Sokali. Jenny is an assistant professor in geophysics, obviously connected to ICME as well. She has been very active in a variety of topics, but specifically her research and her focus is on analyzing risk of disasters and resilience in a variety of different topics. The topics of the presentation today is going to be on eruptions, but she has been involved in a number of different activities where she develops basically algorithms that are compared against observation data for a variety of scales. Now, she has been awarded the Presidential Early Career Award for Scientists and Engineers very recently. That's a great award, a great accomplishment. So thank you, Jenny, for presenting your work here. I'll leave it to you. Thanks.
Thank you so much, Gianluca, for the introduction. I'm always glad to be here, so exciting. In the past few years, I've presented our work on ice sheets. So today I thought I'll do a little bit a different topic just to show you the breadth of what we're doing. As Gianluca said, the theme is always the same. We're working on risk and extreme events, and we're trying to understand why they happen. They actually are ubiquitous across all natural systems, and then we try to use that knowledge to actually reduce the risk they pose. So my talk today is entitled Eruption Forensics. What is eruption forensics and why would we need it? Here at ICME Expo, you tend to hear a lot about big data. That's fabulous. Unfortunately, for extreme events, we have a small data problem. These extreme events are very hard to predict. We don't know when they happen. We don't know where they happen. And even if we did know, like, for example, in this case, you're looking at a picture of Hawaii. If we had our instruments there, the events tend to blow them off the mountain. So it's very difficult to get any data on what's happening. The only data that we have are these tiny little crystals that you see here in the little blow up. And these provide testimony of what happened prior to eruption. Unfortunately, that testimony is very imperfect. Just like in an actual detective story, these little crystals are amazing for being the only source of information we have about what happened prior to eruption, but they don't tend to remember things always quite as well. So what we're doing in this talk, and generally I think in this project, is we try to build models to tease out that information, to try to sort what's valuable from what's maybe not so valuable. So how does that work, and what's the role of modeling in this? Let's first look at the data. So we're doing this for an eruption at Hawaii. Hawaii erupts very often, as you might know. This is Kilauea Iki, the most active volcano. It's currently erupting, actually. Most of the eruptions are very long, easily a year or so. But in between those, we have these beautiful lava fountains. So if you look at the bottom right of the slide, you can see one of these lava fountains. And these lava fountains are really one of the main source of risk, because they cover a lot of land very quickly and are very destructive. So how can we understand what triggers these? So the data that we're trying to leverage here is shown on the left. And these are tiny little crystals. They're literally like a millimeter or so. And what is interesting about these crystals is that they're aligned in a funny way. So when you look at the image, you can see that they kind of have a pretty large angle between them. Fluid dynamically, that's not very likely because in fluids, objects tend to align in a way that reduces the force that they experience, the drag. These crystals clearly don't do that. So why is that? And maybe there's a clue in this very alignment that can tell us about the eruption themselves. I should notice that this kind of alignment is not rare. So you can see here that actually 37% of crystals have this particular alignment. So to understand what this alignment tells us, we've developed two models, an analytical and a numerical model. The analytical model is based on the insight that what crystals do depends on the flow field. So in A, you see a crystal in pure shear. So that's just basically a linear flow field, and the crystal tends to tumble along. In a wave, however, crystals behave very differently. They just assume a particular preferential alignment. And this wave-driven alignment is really at the heart of what I think these little crystals tell us. So if we take into account the fact that a wave gives us an alignment, and we take into account the fact that the crystals themselves have a symmetry, I can show analytically that there's a bifurcation in the governing equation of motions, and that the crystals will align in two ways, as you see here in the center of the slide. I will have this alignment angle phi star, and I will have the opposite angle. So the waves will align the crystals in two orientations, upwards and downwards, separated by the same angle. And you might already guess why that's an interesting result, because it suggests that I will have two types of crystals, the ones upwards and the ones downward oriented. And if they drift together, they form exactly the kind of cluster that we see in the erupted products. So the key conclusion from this analytical model is that I can analytically quantify the flow conditions under which I will see the alignment angles that I observe. So I can tell you that I must have a wave. I can tell you the direction the wave is going. I can tell you the amplitude of the wave as compared to the background shear flow, which is a lot. It's not everything we want to know, but it's a lot better than knowing nothing about the pre-eruptive conditions. So that's the analytical model, and that's great. However, crystals interact, and in Stokes flow, they interact over very long distances. So keep in mind that lava is very highly viscous. It's a very thick liquid. So these tiny crystals, however tiny they might be, actually play a really important role in the flow and dominate the flow behavior at a certain point. So now in a numerical model, we've developed a suite of algorithms that can help us understand the interactions between the crystals. And that's really the novel piece from a numerical point of view. Here we resolve the crystal motion really at the scale of each individual crystal. We're doing it for different geometries. We're doing it for different kind of clustering collision schemes. So that's a lot of work went into that. And it's quite an expensive algorithm. What does that give us? What it gives us is that we can now do a statistical description of what these crystals do. In the analytical model, I can only ever look at one, but there are hundreds of crystals in the conduit. I need to get a better sense of the statistical assemblage. And this is what the numerical simulations can do. So what you see here is on the left in the pure shear, so that's basically a unidirectional flow, the crystals do actually interact, they do collide, and they form little clusters. However, these clusters don't live very long. So you can think of these as tiny little crystals rotating along, crashing into each other, and then separating quickly. On the right-hand side, which is an overlap of wave and shear flow, you can see that the crystals do form these long-lived aggregates, which is really what I need to explain the data. So our statistical analysis of this larger group of crystals suggests the specific conditions under which these aggregates must have formed, which are at very low crystallinity. Even at above 5% crystallinity, the interactions between the individual crystals will destroy this bifurcation in our governing equation. They will destroy the preferential alignment that the wave built. So I need to have a really low crystallinity, and I need to have a wave-dominated flow. And only under these conditions will the crystal be long-lived enough. So what does that tell us about an eruption? Hawaii erupts all the time, which means that in the conduit, as you show here, as you see here, you must have some magma going up, and on the sides, you have some magma going down. That creates an interface with a wave on it. The crystals that we see must have formed at that interface. And we know that that interface had a wave that was propagating downwards at a certain speed, and we know it had a crystallinity of less than 5%. What does that mean? It means that likely what triggered the eruption was slip along that interface. And that's where the multiphysics comes in. Flow is fantastic. I love fluid simulations, but most natural materials can both flow and slide. And our thinking here is that what these crystals tell us is that this lava fountain specifically was probably initiated by a slip of the inner core of this core of upflowing magma that then created this really large shooting lava fountain into the air. So bottom line, I think there's a great value of these kinds of models to really help us understand these little details, tease out the maximum amount of information from the little data we have. They also help us understand a lot about multiphase flow and just how important the interactions between these minuscule little crystals can be. So with that, I would like to thank you and end on one of my favorite quotes: "Look deep into nature and you will understand everything better," by Einstein. Thank you so much.
Thank you very much, Jenny. Very, very interesting presentation, and certainly going from ice sheet last presentation to this is quite a big change. So thank you for sharing this story. Our last speaker is Nusha Jami. Dr. Ajami is the director of urban water policy with the Stanford University Water in the West program. She is an expert in sustainable water resource management, and she has been very active in a variety of contexts. She's actually part of the gubernatorial appointee for the Bay Area Regional Water Quality Control Board, and she's also on a number of academic boards nationally on water science and technology. She received her degree, her PhD in civil and environmental engineering from UC Irvine, and it's a real pleasure to welcome her here. Thank you, and take it away.
Thank you so much, Gianluca. Definitely a shift to a very interesting conversation or talk that Jenny just gave us. I'm going to bring you down to earth, close to the water sources you depend on. This work that I'm presenting here, which is focusing on water security in Anthropocene, was done by my wonderful PhD student, Jose Bolorines, and a colleague at the CE, Ram Rajagopal. California is now again in a drought. You might have seen it in the newspaper. Droughts are these prolonged climatic effects that can impact our water supply sources, but also they can affect the way people respond to these shocks or stressors. We get a lot of media coverage. We see a lot of changing behavior by customers. And while a lot of studies have been done to understand how droughts impact water supplies, not many of them have focused on how demand changes or water use behavior changes during these climatic shocks. So that was the goal for this study. We wanted to see how these external stressors are impacting human behavior in this setting. We are going to focus on Mesa Water District, which is in Southern California. We worked in Mesa Water District to get their water bi-monthly water bills for about 16,000 of their customers for single family and multifamily residentials. This was between 2002 and 18. So we had 17 years of data, 6 readings a year. The data, we wanted to focus on the customers that have been in their household between 2002 and 18 for the entirety of the time. So that brought down the number of customers for us to about 9,000. And then only 8,600 of these people had complete data sets. So while these numbers may sound small, this is about like 900,000 data points that we had to work with. And that is, and the data, and we wanted to focus on the recent severe drought in California between 2002 and 2016. To better understand how people respond to droughts, we built these customer level random forest models based on assuming or using actually some of the known demand drivers. Often demand is assumed to be driven by the weather, the temperature, the precipitation amount, the price of water. People respond to how much they're paying for water, or also unemployment. If people are under financial stress, they may change their behavior. The study period and the policy regimes that we observed during this period was interesting. We used the 2002 to 2012 data to train our random forest models. And then between 2013 and 17, this was divided to 4 distinct policy regimes. 13 to 14, it was a pre-drought period. We were in a drought, pre-policy period. We were in a drought, no policy action. Between 14 2014 and 15, Governor of California asked the residents to change their water use behavior or reduce their water use voluntarily. Between 15 and 16, the drought was in the highest, and governor actually issued the first ever mandatory water use restriction and asking customers to reduce their water use by 25%. And then the drought started sort of, the conditions started improving, and that was the post 2016-17. We were out of the mandatory water use restrictions were lifted. When we took the random forest models, we took the residuals from those models that we built for each one of those customers. And we assumed those residuals are using the water use data that was not driven by the given or known demand drivers. And we looked at how water use has changed over time. We sort of used the change point detection to identify the time and the amount of change in water use, and then aggregated them. Here, I'm going to show you how those change points, the probability of those change points. This graph on the y-axis is showing the probability of change, and the x-axis is the timeline. What you see here is the consumption decrease. So even though the water, you see an sort of the peak here going on a positive direction, the higher the peak, the more water use was reduced. And you see the 4 policy regimes that I discussed. So this is basically that you see most of the people, and then we also divided these customers between the people who use the most amount of water, the top 20%, people who used the lower 80%. These are all single family residentials. And then multifamily residentials are in the yellow at the bottom, that are basically these buildings with multiple units in them. And what you see here is that most of the conservation, especially for the single family residential, what happened during the voluntary restriction. We used the number of articles that was written on the drought in California, used an in-house developed search algorithm called Articulate. We also looked at the Google search indices that sort of in a way correlates with the public awareness, and as people are reading these articles, they're responding to the information they're receiving. And what you see here again is that during this voluntary period, as the number of articles were increasing, people started responding. Then we put these people in different sort of identify different archetypes. What you see is the customer responses to the drought was heterogeneous. It's interesting. I was listening to Jenny, and I was thinking, it's like you know, these are all people who are clustering in different forms and shapes, very similar idea. So you need to understand how they are responding to the drought, and then how they are changing their behavior. What you see is that you have all these customers that change their water use. About 80% of the conserving customers have a negative shift that occurred during the voluntary period. So people reduce their water use. These different sections are showing you the same policy regimes I mentioned. And about 30% of these customers exhibited rebound, meaning they changed their water use, they reduced their water use, and then when the drought was over, they went back to the previous amount of water they were using. To more closely looking at this, we created this density plot. What you see is on the y-axis is a saving that people exhibited, and the rebound effect of how much water how much they rebounded. And what you see is most of the people who saved more ended up not rebounding, so they have made structural changes in their water use. The reason this is important is that we make a lot of decisions about infrastructure, knowing demand and how demand is changing, and often these assume that demand is increasing. However, in this specific study, we were trying to demonstrate that actually demand is quite dynamic, and we should actually focus on how people use water and potentially use that information more actively in supply management. Thank you. And I close with another Einstein quote, so which says we can't solve problems by using the same kind of thinking we used when we created them. Thank you so much.
Thank you very much. I think we're gonna have everybody back now. Yes, here we are. So thank you all for your presentations, for a very interesting session. I do have a few questions here from the audience. Let's get started immediately. The first is for Professor Eric Darve. How do you choose those benchmarks that you're using to compare your algorithm? And if I understand correctly, in each step of the algorithm, a deep neural network is trained based on the set step in the process. Is that correct?
All right. Can I share my screen again? Yeah, just to just quickly show the slides so we know what we're talking about. So yeah, so basically that's correct. So there's the just answering the second part of the question. So we essentially have a deep neural network that gives us already an estimate of the optimal solution, and then this deep neural network is retrained based on this new set of permutations, or new training set that's generated by k-opt. So we don't actually fully train the neural network. We do a couple of epochs, so basically just to kind of nudge the neural network towards this new set, and then we kind of repeat this this process. In terms of the benchmarks, so basically we sort of essentially our sort of contribution was to some extent combining this idea of AlphaGo and k-opt. So essentially we chose benchmark against sort of these methods taken separately. So just R2, which is basically just the AlphaGo method, and then 3-opt. And then in terms of the the sizes, essentially the 6x6 is the we're limited by computational time, so we sort of went essentially as large as we could. And although now we're developing sort of a multi-scale idea where you basically build first a 4x4 set, and then that's a super tile, and then you build a 4x4 set of these super tiles, and then you can repeat this process a couple of times to really generate very large systems. So hopefully that answers the question.
Thank you, Eric.
Yeah.
I have a question for Jenny. Many of the problems that you're working on, and in general, problems that involve really large temporal and spatial scales, are fundamentally limited by our ability to compute. So if you assume that we have, say, 100x increase, next year, a miracle, what would be your first goal? Can you actually take advantage of that and have real impact, or that would be too simplistic in some of your problems?
Yeah, so I think when you think about answering these kinds of questions, the first thing to keep in mind is that you don't want to represent all scales. Like when engineers talk about, bridging different scales, they talk about 2-3 orders of magnitude max. We're talking about 6 to 10 orders of magnitude here. So it just doesn't make sense to try to resolve everything. I think what you need to combine the compute power with some good old-fashioned thinking and come up with a good idea about what matters, right? Like sometimes, for example, right, like you actually need to go down to the crystal scale. And I think this project I presented today is one of those where that's really essential. It's essential because I want to know exactly what I can get out of these crystals in terms of information about pre-eruptive flow conditions. But that doesn't mean I always need to refine, like I always need to go down to that scale, right? So I think more powerful than compute power to me is just good conceptual level thinking. What's really the question you're asking? What is the model that you need for that? And then write a model that really solves the question that you're asking and not a different one. I think that's also really powerful. We're talking about very nonlinear systems here coupled over multiple scales. I think it's important to have a model that is very good at answering the one question you have, not trying to answer all 10 questions or more that you might have on volcanic systems, right? So I think just focus on what's really the biggest scientific opportunity and do that well. I think you can do that now. You can do it with 100x more compute power, even better. That's great. But I think we're often, I think in our field, we're more limited by the scarcity of models and by sort of creative model development than necessarily by compute power.
Brute force. Great. Thank you very much. That's very, very, very interesting. There is another question that has to do with probably all of you in a sense. The question is, in physical system, data is always limited, imprecise, or perhaps simply old. This is rather different than data coming from other sources like web logs, financial transactions, and so on that keep to be very, very quickly updated. So how does this affect your work? And how do algorithms that are perhaps very common and very useful in data science apply in this context? Do you need new algorithms? I don't know who wants to start, but I guess, you know, maybe droughts are more, so maybe you're getting more and more data, unfortunately.
I would say, you know, actually that's a great question, because we try to do that in our studies. We try to take these new data sets that are becoming available and combine them with these old school data sets that we have. And the challenge is, how do you match these data sets? It's not just how much more data you have available, it's just how do you sort of put them together in a meaningful way that you can get information, but you're not over exaggerating your knowledge, or you're not sort of pinning on information that's not accurate. So it is a challenging process. And for us, often this is not about new methods. Sometimes it's about using the same methods in different ways, or finding some similar. So for example, we use a lot of Bayesian modeling, or, you know, sort of address matching. And some of those are actually using the same kind of math that we had long time ago. It just has more data, and you can use it in a more improved way. And I think the computational piece is valuable for us, at least, just because it led us to process a lot of data and sort of update our knowledge and information more periodically, because we have more computational power and we can do things much faster. So I would say, you know, the new data is rich with a lot of information, but I always have a point of caution that not every data is informative, and not every information that you have is what you're looking for. So you should be very, very careful of how you're interpreting the data you're using.
Eric, you want to?
Yeah. That's a very good question. So very happy that you asked this question. So I think when this machine learning and AI sort of started, there was sort of a common chunk of methods that people were kind of using, but now we're getting sort of more advanced, and things are starting to diverge a little bit, and we're realizing that the requirements, the type of data we have, for example, in engineering, is very different from, let's say, Google and so on, and so we do need to use different algorithms. And so there's multiple actually answers to that question. The first one that comes to mind is, this idea of physics-informed learning, where basically you enhance the data using, for example, physical models in terms of differential equations or conservation laws. And so you sort of combine the sort of data-driven approach with this physics modeling, and this allows you to reduce the size of the data set that's needed. The second point was mentioned by Nusha, which is this Bayesian approach. So basically, if you have limited data, then your answer is really, you find sort of a probabilistic or statistical answer, right? Like in stochastic inversing. So the answer is not necessarily just one number, but it's going to be a distribution. Basically, all the states are sort of consistent with the limited data that you have. You essentially have multiple solutions, so you give them some sort of a probabilistic interpretation. And then the other thing that's sort of very special, I think, for engineering is that the data comes from comes from different sources, and there are some qualitative differences. So namely, you can have some experimental data, again, very often limited because it's expensive, takes time, and so on. But also you may have high fidelity simulation data out of supercomputers, also limited by computational time, access to computers, and so on. But for example, this leads to questions like multi-fidelity modeling, where you have sort of data that are related, but that there are differences between these two data, and you cannot just put them in the same bag and sort of mix it up together. You need to account for differences in fidelity levels of fidelity between this data, and combining this information to come up with your best prediction.
Jenny, do you have a comment as well?
Yeah, I would like to add just one quick point. I think, like most points have already been made, but I think generally what I would add is that it's not just like, to me, an algorithm is really a means to an end, right? So then there's the question, what is the end, right? So I think the question about the data is also related to what are you trying to do with the algorithm? And for example, yes, the data on financial markets and behavior might be more up to date, but also those processes change quickly. So for example, we've been working with our county on improving their COVID response in vulnerable communities. And if you look at that data, you look at sort of last year at this time, it's only a year ago, but the data is completely outdated. Like behavior has changed so fundamentally that if you rerun the same models on the current data, you'll find a completely different answer. So I guess what I would add to that is like what is quick or not quick really depends on the system and how long nonlinear it is. And I think of people as being very nonlinear in their behavior sometimes. So I guess what I would, to me, the answer there is, I think what you need is living models. You need a model that you can rerun, that kind of grows with the data, that changes with the data. It's not a question about like running it once and then having an answer that stands forever. I think it's really a question of sort of the model evolving alongside the data set.
Wow, fantastic. Thank you very much, Jenny. This was a very, very good closure to this session. I want to thank again all the three speakers for a very interesting and very diverse set of presentation and discussion. This basically concludes the presentation sessions of the conference.